Hello students, in this session we will discuss about superelevation, why it is provided and analysis of superelevation at horizontal curve. So we know that when the vehicle negotiates the horizontal curve, the centrifugal force will be developed. In order to counteract the effect of centrifugal force and to reduce the tendency of the vehicles to overturn or skid, the outer edge of the pavement is raised with respect to the inner edge. Let us consider this as a horizontal curve. The pavement is provided at the horizontal curve. So in the horizontal curve, this will be the outer side and this will be the inner side of the horizontal curve. So when the pavement is constructed here in such a way that the outer end of the pavement will be raised with respect to the inner edge. This transverse inclination to the pavement surface is known as the superelevation. We can also call it as the cant or banking. The rate of superelevation provided is expressed in terms of E as the ratio of height of outer edge with respect to the horizontal width. So here E is nothing but the horizontal width that is provided, and ML in this picture will represent the horizontal width. So if you consider that E will be superelevation can be taken as tan theta, and if you work out for tan theta will be the opposite side, that is NL divided by ML. But here we don't know the value of this ML. So at very small angle, the theta here will be very small. At small angle, tan theta will be approximately equal to sin theta. So the sin theta will be opposite NL divided by the hypotenuse value, that is hypotenuse is ML. So we know what is the rate of superelevation provided. The height amount raised will be E, and ML is nothing but the width of the pavement, and that can be taken as the B. So with this we can determine how much rise has to be provided. If you know the value of superelevation, E value, the maximum allowable superelevation at the horizontal curve, we can determine how much is the raise of pavement with respect to the inner side. Next, we'll move on to the analysis of superelevation. To analyze the superelevation, to determine the equilibrium condition and what should be the rate of superelevation has to be provided at the horizontal curve to counteract the effect of centrifugal force in order to overcome the vehicle from overturning or the lateral skidding. First, let us consider the various forces acting on the vehicle at the horizontal curves. The picture here illustrates the various forces that are acting. In the previous session, we have already discussed the forces that are acting on the vehicle when it negotiates the horizontal curves. We will have the three major components. The first one will be the centrifugal force that is developed, that is P, which acts in the perpendicularly outward direction. And then we have the weight component W, which will act in the perpendicular downward direction. And along with that, we will have the friction that is developed because of the interaction between the tire and the pavement surface. Now let us consider all these forces that are acting on the vehicle when it negotiates the horizontal curves. But here we need to considering the superelevation. In the previously, when we discussed the horizontal curve, we discussed the forces acting on the vehicle without superelevation. But now here we have raised the pavement with respect to the inner edge by an amount of E, and angle suspended, we will take it as the theta. If this is theta, and next is we need to consider the various forces that are acting on the vehicle on the when it negotiates the horizontal curve of R meter, and which is the speed of V meter per second. So now here as I mentioned, we have the centrifugal force which is acting in the perpendicularly outward direction. W is the weight of the vehicle which is acting in the perpendicularly downward direction. F is the frictional force between the wheels and the pavement along the surface in the inward direction. So here you have to note that the weight component will act in a perpendicularly downward direction to the horizontal surface. So this is the horizontal surface. So now the original forces what we have to consider that will act perpendicular to the horizontal surface, and similarly here the centrifugal force will act in the perpendicularly outward direction with respect to the horizontal. But now to analyze the superelevation, we have to consider what is the force component which is perpendicular to the pavement edge. So this is the pavement edge. So now we have to analyze the forces with respect to the pavement surface. So now we have to consider we have to resolute the forces, and we need to consider what is the force component which with respect to the pavement surfaces. So if we consider that, we can see here, if this is the theta, the force component perpendicular to the pavement surface will be P cos theta. And also we have the same, if we resolve the P in the vertical direction, here along with that we will have P sin theta. This is the force component with respect to the centrifugal force. We are just resolving the forces in the horizontal and vertical direction. Similarly, similar how we resolve for the force, we need to centrifugal force developed. We need to resolve the forces for the weight component. So for the weight component which is perpendicular to the pavement surface will be W cos theta, and the horizontal component here will be W sin theta. So now you have to see that. So for which side it is suspending the angle, the particular side will be the cos theta and other side will be the sin theta. Okay, so please make sure, make a note that. So what we have written, I have written in the blue color, it is the component of weight with respect resolving with respect to horizontal and vertical direction, and which is in the purple, which is the resolving the centrifugal force in the horizontal and vertical direction respectively. And along with these two forces we have the frictional forces. It is, you can see here, frictional forces Fa and frictional forces Fb, which is developed due to the interaction between the wheels and the pavement along the surface in the inward direction. So frictional component will be developed in the inward direction. The next is to analyze the superelevation. We have to consider the equilibrium of all these forces. So what we are doing is we are just resolving at the inter-equilibrium condition. We are resolving all the forces parallel to the surface. So here when I say the surface, it is surface which pavement surface what we are considering, not the ground surface. Okay, so first we'll resolve all the forces parallel to the pavement surface. So in the horizontal direction we have two components, that is the P cos theta and W sin theta, and similarly in the vertical direction we had two components, that is W cos theta and P sin theta, and along with that we have component Fa and Fb we need to resolve. So let us first consider all the forces parallel to the surface. So the forces which are parallel to the surface are P cos theta is equal to P cos theta is equal to, and here when we resolve the weight component we have to see here that it acts in the opposite direction. Since the theta is making here, angle is suspended with respect to this. This is the weight component. When we resolve it, so here we will have the W sin theta, which will be in the opposite direction. So here the value become minus sin theta. So the forces which are acting in the horizontal direction will be P cos theta minus W sin theta will be equal to the frictional forces which are in the opposite direction. That becomes Fk plus Fb. So if you resolve taking the positives to one side, that becomes P cos theta is equal to W sin theta Fa plus Fb. Here Fa and Fb we can take it as frictional force into the Ra and Rb resultant which has developed. Okay, that we have already discussed how these things will come. So resolving further, simplifying it, W cos theta will be Ra and Rb is nothing but the resultant force which is acting in the perpendicular direction to the pavement surface. So this will be the resultant RA and RB. So now, so RA and RB is nothing but the forces which are acting in the upward direction. So we'll consider all the forces which are acting in the vertical direction. Now if you take the vertical direction, we have RA and RB, that's the resultant forces, and along with that we have these two components that will be equal to W cos theta plus P sin theta. So that is what is been substituted here. In the place of RA and RB, we are substituting with the forces which are acting in the downward direction, that is W cos theta and P sin theta. So here, where W is the weight of the vehicle, P is the centrifugal force developed, F is the frictional coefficient, and theta is the transverse slope provided due to the super elevation. Now here, the entire equation is divided by W cos theta. This is just for the further simplification. So when we further simplify it, it will become P by W. P by W is nothing but the centrifugal ratio. Centrifugal ratio will be equal to, so W gets cancelled, sin by cos is tan theta. So here also W cancels, F remains, and here also F into P by W tan theta. Sin theta by cos theta will be equal to tan theta. Now taking P by W on one side, P by W is equal to 1 minus tan theta, which is equal to tan theta plus F. So thus the centrifugal force P by W will be equal to tan theta plus F divided by 1 minus tan theta. So we have already derived expression where centrifugal force can be expressed as F is equal to V square divided by GI. This is the condition what we have derived when we analyze the horizontal centrifugal force developed at the horizontal curves. So now by using these substituting equation 1 in the earlier equation what we had obtained, V square by GR will be equal to tan theta plus F divided by 1 minus tan theta. So this is an expression for super elevation, but normally the coefficient of friction developed at the horizontal curve, we call it as the lateral friction, and IRC recommend to consider the lateral friction value of 0.15, and the theta will be very small, and that should be less than 4 degree. So by substituting this value, 1 minus tan theta will be approximately equal to 1, and for tan theta, for small angle theta, tan theta will become sin theta, that is E by B. We can take a considered as the super elevation E. So substituting all these, we are substituting the value of F as 0.5, 1 minus tan theta is equal to 1, and we are also substituting the value E by B is equal to E. So by equating all these value, we have got E plus F. So tan theta, we have substituting it as E. Okay, at small angle tan theta is approximately equal to sin theta value will become E. So we are substituting in place of tan theta, we are replacing it with the E. So E plus F, the denominator, this portion become the value 1. So tan theta will be converted to E. So E plus F will be equal to V square by GR. So this is an expression for super elevation design. Now here E is the rate of super elevation and F is the coefficient of lateral friction, that is 0.15, and V is the speed of the vehicle in meter per second, and R is the radius of curve, and G is the acceleration due to gravity. We can take the value as 9.8 meter per second square. So this expression will be used when we design the super elevation. So here at the horizontal curve, we will be knowing IRC recommends the maximum super elevation value can be taken as 0.07, and F value, maximum value, it can attain as 0.5. So now when we design the horizontal curve, we have to we'll look at before moving to the design of the horizontal curve. So the previous expression what we have derived, that is the speed value is in terms of meter per second square. So generally all our speed value will be in kmph. If you convert that into the kmph, the equation becomes E plus F is equal to V square divided by 127 R. So here V value is speed of vehicle in kmph, and is, as I mentioned earlier, maximum rate of elevation is 7% or the 0.07, and minimum coefficient of friction value will be 0.15. In some situation, particularly at intersection, it is not possible to provide the super elevation, and in such cases friction alone will counteract the centrifugal force fully. So the allowable speed at that case, so without here E value becomes 0. So here the what centrifugal force developed has to be counteracted only by the frictional value. So now we cannot increase the friction to so much extent. So what we have to do is, instead of increasing the friction to the some extent value, we have to reduce the speed at such restricted condition. The reduction in speed can be taken as V is equal to square root of, so here the equation is simple, it becomes V square divided by 127 R. When the E value is 0, considering the F value maximum super elevation as 0.15, we have to determine what is the restricted speed at the the horizontal curve. So this is how we have to consider, we have to analyze the various forces that are acting on the horizontal curve, and will derive an expression for super elevation. In the next session, we'll see the how to design the super elevation at the horizontal curves. Thank you.